Welcome back, this is Gus. Today's spooky episode is about capacitive sensing. I have 3 examples for you, and I'm going to try to explain it really quick. There's a lot involved when we talk about capacitive sensing, so I want to cover only what's really important for our viewers. In this first example, I have a Fez Cobra connected to a screen through 2 wires to a resistor, and let me show you. I want to show you the demo first and then explain what's going on. It's easier, more interesting this way, easier to explain. So all I have is a ground wire, a signal wire going to a resistor. What's happening here? In this demo, I'm showing a little graph on the screen. So when I touch the resistor, you can see this changing, coming down. So the levels are changing. I'm using this instead of showing text, I'm showing graphs because it's easier to see. So touch it again, this go low, and now when I'm close to the wire, that still changes as well. So I'm over here, I'm not touching the wire, I'm not touching the actual signal on the resistor. I'm just touching the wire, and you can see it's going down. Not as much, but it's going down. So what's happening? And how am I measuring this? We added a method in our library to handle this for you, so you don't have to really do it manually. You can just use our PulseFeedback. And the way capacitive sensing work, it uses the capacitance in our body, and it charges, for starter, it charges a capacitor that is in the circuit somewhere. Some kind of capacitance in the circuit, and there is a resistor. So between the resistor and the capacitor, there is time. The resistor and the capacitor size determine the time needed to discharge that capacitor. So if I have a circuit that clicks on and charges the capacitor completely, and then I disconnect that voltage off the capacitor and wait for it to discharge, that's going to happen over time. The smaller the resistor, the quicker it discharges. The smaller the capacitor, the quicker it discharges. So in this example over here, our program internally, it's turning the signal high on this signal right here on the green wire. It's coming on for a short time, or you can set that in the code. And then after it sets it on, it makes that pin an input. It releases it. And then that pin is going to discharge over time. I do not have a capacitor as in this example. You can add a capacitor, but I did not add that to show you that this will also work without a capacitor because everything has capacitance to it. That's normal. So the pin, even though there's no capacitor on the pin takes time to discharge. I have this resistor. This is like a 1 mega ohm. It's a very large resistor. A smaller resistor will make it, considering the capacitance I have is extremely small. I don't even have a capacitor. This is the capacitance of the pin itself. So considering this is really small, I used a very, very large resistor so this will take some amount of time that I can measure in my code. This is about 1 mega ohm. That's connected between the pin and ground. So every time the signal kicks on, it sets it to high, to 3.3 volts, and then sometime later, that's I set in the code, it shuts off the voltage and makes that pin an input really quick, and start observing the pin and seeing when would that pin fall down enough to be a low. And I'm taking that measurement and showing it on the screen. Now, touching the wire, touching the signal, it changes that time. And through that time, I can determine if there is a touch or not. It doesn't have to be physical touch because the way capacitance work, you're not measuring the resistor, you're measuring capacitance. And depending, like 2 elements basically have a charge between them. And this is how capacitors are created. This is like, we're talking about extreme basics here. This is not exactly the right terminology, just so it's easier to understand. Now, this is good for simple things. I can connect this to, I've seen it on YouTube where they have capacitance input, where they connect the wire to like fruits, and then you can touch the fruits, and you're measuring them, and you can play music that way. So this is interesting to have fun with the kids, or something that we can have fun with, especially now with the Halloween coming up this weekend. But I want to show you another example where if you have something more serious, you would probably be using a chip that handles all this for you. Usually they are I2C, so over I2C bus, you would be talking to registers, digitally talking to the chip. And the chip will read the value. So you would set thresholds. We saw how on the screen we had levels, but these don't mean much. The chip would take multiple samples, will filter those samples. Well, you would set a threshold for touched or untouched. Some of them even sense when you're close to the circuit. So maybe on a TV set that you may already own, when you come close to the TV, a backlight will come on to show volume up, volume down. And then the volume up, volume down buttons are actually not buttons. They are capacitive inputs. So they are behind the plastic. You don't have to touch them. You just have to be close enough, and they set the thresholds. So when you're close enough, they detect that you're close, and it works just like buttons. This example over here, I have two forms of capacitance inputs. The first form is through this shield by Sparkfun. It's called the touch shield, and this tiny chip on here, you would connect the chip to pads or objects or whatever you want to connect it to, and you would use it through I2C to detect that there is a touch on these pads. So this is showing P2 true, P1 is false, P3 is false. If I press 1, P1 true, P2 false. The other example I have on here is from the capacitive screen. This screen uses almost even a fancier form of capacitive sensing, and this is what you have on your phone. It has multiple capacitors all across, or multiple sensors all across. And through the different sensors, it can figure out where you're touching. It can even detect multiple touches. I believe this screen can handle up to 5 touches. I'm only reading the first one. And this is I2C, still same as this chipset. So the screen that sits on top, this is not the LCD. So keep that in mind when you look at LCDs. The touch on top, it might be connected to the same cable on the bottom. So you have one cable. But if you look at the side, on your display, you would see that they are separate. So in this display, they are separate. So this is the cable that goes to the capacitive screen. And over here, where the square is, there is a very tiny circuit that has a chip similar to this one that is handling the touch. If I move my finger on the screen, the closer I am to the upper left corner, the smaller the numbers get. And then the other way, if I go to the lower right corners, the numbers increase to the maximum. I hope you enjoyed this video. If you celebrate Halloween, I hope you enjoyed the added spooky touch we added to this episode. Happy Halloween, and we'll see you next week.